Hello everyone, my name is Gonzalo Ferrada. I'm a PhD student at the University of Iowa, and today I will present about a new biomass burning emission inventory that I have been working on lately. Why do we care about the smoke in the atmosphere? Well, globally, fires are responsible for the release of around 2 petagrams of carbon emissions each year. In this figure, you can see the major regions that contribute the most to biomass burning emissions. Many of these fires are man-made burns that happen seasonally every year. Among all the gases released, you also have several greenhouse gases, such as carbon monoxide, carbon dioxide, methane, water vapor, etc., that contribute to global warming. Also, fires release hydrocarbons that can serve as ozone precursors. In addition, particles interact with solar radiation in a way that they can absorb it or scatter it. On top of this, some of these particles can serve as cloud condensation nuclei that alters the formation of clouds and precipitation processes. And of course, when urban areas are exposed to poor air quality episodes, you can create health emergencies and interference with human activities such as the economy. So how do we quantify the emissions that fires produce? There are several biomass burning emission inventories that rely on hotspot detections from satellites. Here I am showing 4 major inventories and some of their characteristics. For example, GFED and FIN use the bottom-up approach, which uses estimation of burn area to calculate emissions. On the other hand, QFED and GFAS use the top-down approach, which make use of the fire radiative power from satellites. However, these inventories have some limitations, especially regarding their product resolution, in which, with the exception of FIN, are graded at no higher resolution than 10 kilometers. This is a problem when using these emissions on high-resolution model simulations, because fires can be misplaced. So we created VFEI, which stands for VIIRS-based fire emission inventory. We use the top-down approach and calculate emissions for different species by using this equation, and that is the same that is used in QFED and GFAS. We used the updated emissions factors from ANDRE 2019 to generate emissions for more than 40 species classified in 6 different biomes. The reason we are using VIIRS is because of some of these sensors' advantages when comparing with MODIS. The paper from Lee et al. 2018 shows that FRP values from VIIRS are comparable to those of MODIS, plus the advantages of having less distortion at the edges of the swath, higher resolution, which is ideal for detecting small fires, and no data gaps in the tropics. The results are daily global emissions at resolutions of around 500 meters. We have produced emissions since early 2012 to 2020 based on VIIRS NPP. Here you see daily emissions for 2017, and the purple colors represent low emissions while the yellow colors represent high emissions. Sometimes large yellow circles appear, and they represent very high FRPs. Our inventory will be publicly available in a website that we are preparing, and the data will come in 2 different formats. One is a text file that will list all the fires and their emissions at 500-meter resolution. These text files are ready to be pre-processed for WRF-Chem. Also, the emissions will be available as netCDF, but we decreased the resolution to around 0.1 degrees to save storage space. Here is an example of misplacement of fires in a model grid. This shows a time series for early August 2019 of a large fire that occurred in Washington state. This is how QFED maps this fire in its 0.1 degree resolution. However, if we map this fire into a 2.5 kilometer model grid, this is how it looks like. You can see that the fire appears as 4 or 5 different fires because the model tries to find the closest grid box for each QFED fire. Now, this is how VFEI maps the same fire. You can notice that much more detail in the variability and progression of the fire at this high resolution. And when we map this into the model grid, this is the result. The advantages are evident, and this is especially important when simulating fires in complex topography, because if you have a fire misplaced, then the smoke can be subject to different local circulation patterns and plume development. We compared our VFEI emissions to other 4 inventories I mentioned before. These figures show the average annual emissions in teragrams per year of selected species that are shown in each column. Each row represents different regions of the world that you can locate in the map.
So here we have GFET in black, FIN version 1.5 in brown, FIN version 2.2 in orange, QFET in blue, GFAS in green, and VFEI in red. In the top there are the global average emissions, and you can see that VFEI is very much like the other inventories, not only in this globally, but in almost all regions. However, we make use of the emission factors for boreal forests introduced recently by Andre in 2019, and the regions of Siberia and Boreal America are the ones with the major differences with respect to the other inventories. So probably there is still some uncertainties for this biome. But just to remember, all the inventories are estimations and no observations are presented in this figure. We also compared the seasonality of fires, and the map shows the month of the year with the highest emissions in each grid box. Also, the results are very much comparable to the other inventories. To test the VFEI emissions, we conducted simulations using WRF-Chem with Mozart chemistry and mosaic aerosols for Southern Africa, because it's the region that has the most intense fire activity in the world, and also a NASA field experiment called Oracles was conducted there between 2016 and 2018. This simulation was at 28-kilometer resolution. The map showed the domain of this simulation and the total carbon emissions, and the plot below shows a time series comparing the different inventories. This figure shows a comparison of MODIS MAIAC AOD versus our simulations that we name WRF VFEI, but also against CAMS reanalysis and MERA2 reanalysis. In the top, we show the average AOD from each dataset during September 2016. In the bottom left is a map showing the number of observations available that were weighted in this average. Then we show the biases from each model and reanalysis with respect to MODIS MAIAC. You can see that WRF VFEI is able to reproduce the shape of the plume in the locations shown in MODIS MAIAC, but there are possible overestimations on AOD in the region of Angola, which can go up to 0.2 in average. However, MODIS MAIAC divides the world in different tiles or regions, and they apply different filterings and corrections to the AOD retrievals. For example, you can notice a straight line around 18 degrees south that divides different tiles, and therefore you see a sharp difference between the AODs produced. To prove this point, we also use AODs from AERONET stations across this region. Here we present the data as time series for September 2016, where the black dots represent the AOD from AERONET, the red line and red dots represent the data from the WRF VFEI simulation, and also we included the AOD from MODIS MAIAC shown as blue crosses. You can see that in the stations in the south, such as Windport and Bonanza, the model performs quite well with correlations above 0.86 and low biases, while it seems that MODIS MAIAC greatly underestimates the AOD in these regions. The same is true in the station that is closer to the fire emission source, such as Monguin in Zambia and Lubango in Angola, this latter one with biases of around 0.09. And the scatter plot here shows how the model overall performs when compared against all the stations shown here in the map, not only the 6, but all the ones that are in purple. And the biases here are around of 0.03 if we take the whole matrix. When we compare against the airborne data from oracles, we also see some biases, but in general, the fittings and correlations are above 0.75 in the primarily emitted species, such as carbon monoxide, black carbon, and organic carbon. The other secondary species, such as ozone, ammonium, and sulfate, show higher biases and lower correlations, but this depends more in the model itself and its parameterizations rather than in the VFEI emission inventory. However, we acknowledge that this is more difficult to prove. It's important to note that most of these flights were conducted at altitudes between 4 and 8 kilometers, where the model has thick layers that can also introduce errors when extracting the data at such altitudes. In summary, we created a biomass burning emission inventory that we call VFEI, and it's based on VIIRS fire radiative power. VFEI produces emissions for more than 40 species at very high resolutions, and results are comparable to other inventories. We conducted simulations over Southern Africa for September 2016, and comparison against AOD from MODIS MAIAC and AERONET sites
showed overall good agreement with somewhat high correlations and biases around 10%. Correlations were also high when comparing against airborne data from Oracle's campaign for carbon monoxide, organic carbon, and black carbon. We are also conducting other simulations for other regions to try to assess the model as much as possible. Thanks for your attention, and I will be happy to respond any questions and suggestions during the conference. Bye.